In this example, it's a good chance to practice your skills. If you had the inverse Laplace transform of the negative exponential over s squared plus 4, think your way through the application of this transform element for the function that you'd get out of this particular example. We'll leave this here for 5 seconds, and then we'll walk through the calculations. All right, what we would do to make this as clear as possible is break it into the two pieces, the negative exponential, and then explicitly the other part, the part without the exponential. What we look at when we see our table is that we have the Laplace transform of k over s squared plus k squared. What we see in our table is the Laplace transform of k over s squared plus k squared. Rather, the inverse of that would be sine of kt. So that's what we're using as a building block. Notice that's not quite what we have here, so we use our other tricks. We say, I don't want a 1 on top, I want a 2 on top to match this expression here. Well, I can't just go adding 2's because I want to. We have to balance it by dividing by 2, and that's what we would get. With the next step, we could bring that half out front, and then we could say, all right, what's the impact of this e to the negative pi s? We would have a u pi, the step function that's on at time pi, and then we would have the transform of the k over s squared plus k squared sine. So it'll be sine of 2t, except every t at the innermost level is replaced by t minus whatever the exponential coefficient was, so t minus pi here. So this function, when we inverse transform it, gives us a half to make the coefficients work out, a step function that's on at pi, and then sine of 2 in brackets t minus pi. When would we ever encounter a function like that? Well, keep in mind what this looks like. This step function is something that turns on at time pi. So if we labeled our points here as pi and 2 pi, there is literally nothing happening for the first 3.14 seconds if we're using the usual units. So we've got nothing happening, and then this t minus pi in the inside actually translates to the sine function starting at that instant. We see a half out front, so we have an amplitude of a half, and this 2 is our frequency in radians per second, or if it's also a multiplier that changes the period, we can figure out that the period in this case here is going to be half as long. It's 2 pi by default, but we divide by that value. So the period is just pi. So between here and here we get 1 full cycle. And then we'd have the graph going on from there. So this function, which is the sine function, shifted to the right by pi, but off for those first pi instants, nothing, 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 then the sine starts, would be perfectly represented, or is what we would get if we took the inverse transform of this fairly complicated e to the negative pi s squared over s squared plus 4. In a similar vein, if we took the inverse transform here, let's break it out into the e to the negative 2s times the rest of it. With this particular example, to find the inverse of this portion here, we need to use partial fractions. So if we break that part of the problem out, we have 1 over s minus 1 times s minus 2 on the denominator, that could be rewritten as a over s minus 1 plus b over s minus 2. If we cross multiply like crazy, we would end up with this form here. And that we can easily solve for a and b. What we can do is let s equal 2, for example. That would give us 1. It would wipe that out, and we'd have b. Damn it. We could sub in s equals 2, for example. That would make this term 0, so we'd simply have 1 equals b times 2 minus 1, or b equals 1. That's pretty nice. Alternatively, we could let s equal 1. That would make this term very simple, and we'd have 1 equals a times 1 minus 2, and so b would equal, a. So a would equal negative 1. Now, how does that help us? Well, if we go back to the original inverse Laplace transform, we're still trying to do that. We're now doing it for e to the negative 2s times the decomposed version of this, a over s minus 1. And what we're going to do is expand this out. Actually, let's do this in stages. We'll do this in stages, so literally this partial fraction decomposition gives us that sum of fractions, that sum of rational functions. And then what we're going to do is distribute that exponential into both terms. So we're going to have the inverse Laplace of e to the negative 2s, 1 over s minus 1, plus the inverse is linear, so we can do it separately, e to the negative 2s, 1 over s minus 2. At this stage here, we can apply our rule from before, Laplace transform inverse. When we have an e to the negative as times some function we know the transform of, we get the step function on at a times the inverse times f of t minus a. All the t's that we would have gotten replaced with t minus a. What does that give us here? E to the negative 2s gives us a u2. This transform here is of e to the positive 1t, but we're going to replace the t with t minus 2. Likewise, we have another step function u2, and now it's times 1 over s minus 2. The transform of that is the negative. The transform of that is the exponential e to the 2t, but the t at the innermost level, so put brackets around the t and replace it by a t minus 2, we would have that. With the one caveat that we lost a negative sign. There's a negative here, so this would be negative out front of that, and we'd end up with a negative out front of this term here. So what we'd have again is exponentials that are shifted to the right, but that only turn on at time 2. It's important to note parts of the process that we went through there. When we're doing the inverse Laplace with step or piecewise functions, what you're going to want to do is group or gather any of the exponentials that have the same power to them with an s in them. those are the functions that are going to have the same step function, the same on time. The second most important thing and most common mistake students make at this stage is that when they're doing the partial fractions, they use the exponential in the partial fractions. I've seen this, I can't tell you how many times. This over s minus 1, s minus 2 equals a s minus 1 plus b over s minus 2. That is, what's the word? Wrong. You can't do that. Partial fractions only works if we're decomposing polynomials over polynomials. So how do you deal with that? Well, what you do is you take this e to the negative 10s. It's there. You can't get rid of it. But you put it as a over s minus 1 plus b over s minus 2 all times e to the negative 10s. You bring this e to the negative 10s outside. That is the right way to handle it. So just be aware, don't try any shortcuts on your partial fractions. Treat it as polynomials over polynomials. That's when it works. If there's an exponential, that's fine. Just leave it outside and we'll take care of it in the final inverse step.